All right, everyone. Today we're going to be moving along and finding limits. Today is going to be our first introduction to finding limits using algebraic techniques. So over the past couple of days, we've been taking a graphic approach. We've been looking at tables. We've been creating piecewise functions and evaluating limits. But today we are going to be using algebraic techniques to find limits. So really today we're going to be dealing more with, it might just be some of our parent functions such as quadratics. We might be dealing with rational functions as well. So for our first example here, we're going to find the limit as x approaches 2 for the function x squared minus 1. Now, I know right away that this limit is equal to 3. X squared minus 1 is a parabola. It doesn't have any stretch, no horizontal shifts. It just has a vertical shift of down 1. Our vertex is at 0, -1. When x is equal to positive 2, we would have the point 2, 3. And as we approach 2 from both the left and the right with our quadratic, we can see that the left-hand limit is equal to the right-hand limit. Therefore, our limit exists being positive 3. Quick way to check this would be if we evaluated x squared minus 1 at 2. 4 minus 1 is 3. Oftentimes, direct substitution is a great way to find your limit. So we use direct substitution, and this should always be your first choice. Now, if direct substitution doesn't work, we'll have to try something else, but a lot of the times if we have a parent function, or maybe it's even a rational function that might have some discontinuities like an asymptote, or where the limit would be where the limit approaches infinity and doesn't exist, there's still times where direct substitution will work. For example, if we want to find the limit as x approaches 1 for the rational function 3x plus 4 over x squared plus x, looking at that, it might be hard for us to picture what the function looks like, but through direct substitution, we end up with a final answer of 7 over 2. So for the function 3x plus 4 over x squared plus x, the limit as x approaches 1 is 7 over 2. The function is defined there, and the left-hand limit and the right-hand limit approach the same place. So direct substitution is always the first thing you should check. So if we want to find the limit as x approaches 1 for x squared plus x over x squared minus 1. We're going to try direct substitution first. We'll get 2 over 0. You can't divide by 0, therefore the limit does not exist. We'll talk about a little later on this unit when we get to discontinuities. But if we were to factor the denominator, we'd have x plus 1 and x minus 1. You actually have a vertical asymptote when x is equal to positive 1. So if you remember graphing rational functions from first semester, we have a vertical asymptote at 1. We know that as functions approach asymptotes, the limit does not exist. So I'm going to add a page here to the notes, and we'll keep scrolling along. But just to kind of sum things up right now, when you're finding limits algebraically, the first thing you want to do is always check to see if direct substitution reveals the limit for your function. Remember, if we got 0 over 2, that limit would be 0, but 2 divided by 0, we can't divide by 0, therefore the limit does not exist. So in our next example, we will try to find the limit again as x approaches 1, but for a different function this time. Now we have x squared minus x over x squared minus 1. We try direct substitution first. Substituting in positive 1, we end up with 0 over 0. Now 0 over 0, that means that this is indeterminate. 0 divided by 0 is not 0. 0 divided by 0 does not mean that the limit doesn't exist. It means we need to investigate a little bit further. So we have a rational function just like we would have done with graphing, it's always easier if we can simplify the rational function first. Then we can really take a look at what the function is doing, the types of asymptotes we have, where the function isn't defined. So we should be able to recognize here, and it's important that we continue to write the limit as x approaches 1 out in front of our function. Notation-wise, it's proper to keep that. You can't drop the limit until you actually go ahead and evaluate the function. I notice that x is a common factor in the numerator, so I'm going to factor out an x. The denominator can be factored into difference of squares. We have that factor of x minus 1 cancels. We are left with an x in the numerator, so the limit as x approaches 1 for x over x plus 1. Now with direct substitution, replace the x's with 1, we get a limit of 1/2. So anytime you get a case where direct substitution is indeterminate, that tells us that we need to go ahead and investigate a little bit further. So we want to make sure that when we do that, we're using our factoring techniques to verify, right? I got 0 over 0. Let's use our factoring techniques to verify what that limit would actually be. So we can do one more example here. So we're going to go ahead and find the limit here then as x approaches 4. We have x cubed minus 64 in the numerator, x cubed minus 4x squared plus x minus 4 in the denominator. The first thing we should always check would be direct substitution. When you substitute in a 4, we're going to get 0 over 0. Remember, again, that's not 0. That means it is indeterminate, and we need to do some further investigation. Further investigation involves us simplifying. In the numerator, we have difference of cubes. We have x to the power of 3. The cubed root of 64 would be negative 4. So we have x minus 4, x squared, plus 4x plus 16. So I've used the difference of cubes. Remember, the first sign always stays the same. It's subtraction. X and x squared would give us x cubed. And we have plus 4x and plus 16. That last term always has to be positive, because in order for us to have a negative 4 and a positive 16, that gets us back to negative 64. So we've gone ahead and we have factored the numerator. We can factor the denominator. We have 4 terms. We are going to factor by grouping. You can factor out an x squared in the first quantity. You can factor out a positive 1 in the second quantity because there's no common factor outside of 1. Pulling out an x squared and a 1 leaves you with x minus 4. We can simplify those factors, and now we're finding the limit as x approaches 4 for x squared plus 4x plus 16. We can't factor that any further. We can't factor x squared plus 1 any further. So now through direct substitution, you end up with 16 plus 16 plus 16, substituting in that 4 over 4 squared plus 1, that's 17. The limit as x approaches 4 would be 48 over 17. Remember, you need to keep that limit notation until you use direct substitution. And we can do one more example here. We've got a little bit more time. We'll do one more here that just makes you, we talked a little bit about it earlier, but I'll just have you guys go ahead and do it. We have x squared minus 5x plus 6 over x squared plus 4x plus 4. Now, we could go ahead and factor, but I don't think you're going to be able to factor anything here. Oh, actually you could, but some people jump to factoring right away. Don't do that. There's no need. Sure, I can do that. X plus 2 and x plus 2. And you're going to see no factors cancel anyways. The first thing we always should check should just be direct substitution. So if we go ahead and use direct substitution, and I replace all of those x's with a 2, we end up with 0 over 16. We can do 0 divided by 16. The limit as x approaches 2 for that function would be 0. So remember, if you end up with 0 over 0, then that's indeterminate. We're going to need to do a little further investigation by factoring. If you can use direct substitution, you can always do that first. Great. Anything over 0, the limit does not exist. 0 in the numerator divided by a number that is equal to 0 for your limits. Hopefully those examples give you a good start for tonight's practice. You can spend the rest of the time working on day 4. If you are not caught up with day 2 and 3, please make sure you are completing those as well. Enjoy your long weekend.